Hi everyone, today a video on alkenes and specifically the reactions of alkenes. So alkenes will burn in air. We can combust alkenes like we can alkanes, but they're quite often not used as fuels because their reactivity makes them much more useful for other purposes. They're much more widely used as a synthetic chemical, really as a chemical that can be used to turn into lots of other different types of chemicals. And so we can write a standard combustion equation, for example, taking ethene, reacting it in complete combustion with oxygen, and with a complete combustion gives us carbon dioxide and water as our combustion products. And we have to balance our equation. Again, the easiest way to balance the equation is to always balance your carbons first, because they only exist in the alkene and CO2, and then to balance your oxygen and hydrogen atoms at last. Now, the reaction of alkenes are typically electrophilic addition reactions. We talked last time about the fact that alkenes have high electron density. The 4 electrons in the carbon-carbon double bond make it very, very electron dense, and so they're very easily attacked by electrophiles, these electron deficient species. And so they're addition reactions because the alkene is unsaturated. We can add across the double bond, and because it involves an electrophile, it's electrophilic addition. And so electrophiles are attracted towards this high electron density, and a bond can be formed by using 2 of the 4 electrons in that carbon-carbon double bond, the 2 in the pi bond. Remember from the last video in this series that the pi component of the bond was weaker than the sigma component, and so it's the pi bond bit that breaks. And as I said before, while the pi bond is technically less strong than the sigma bond, the combined effect of it means that a CC double bond in an alkene is stronger than just in alkanes by just less than twice the amount. But the mechanism for these electrophilic addition reactions is always the same. And so it looks like maybe there's quite a lot of mechanisms to learn, but actually it doesn't matter whether the alkene changes or the electrophile changes, the mechanism is always the same. So we have an alkene. This is our nucleophile. This is our region of high electron density. Remember, a nucleophile is an electron pair donor, electrophile, and electron pair acceptor. So our alkene is our nucleophile. It's going to donate, not a lone pair, but donate our electron pair from the pi bond of our alkene to our electrophile. So the electrophile I'm using in this case is HBr. Now HBr can act as an electrophile because there's a permanent dipole in HBr. Bromine is much more electronegative than hydrogen, so we have this polar bond where we have our Br minus, delta minus, our sort of partial negative charge, and our H delta plus, our partial positive charge. And so this fact that it's got this partial positive charge means that it can act as an electrophile. And so our first set of arrows is to draw an arrow from the CC double bond, from our electron dense region, to the H atom, the delta plus atom. And then hydrogen can only have one bond. If we're forming a bond to it, we have to break the bond that's already made to it. And so we have this very familiar arrow here of an arrow starting in the middle of a sigma bond and ending up at an electronegative atom such as the bromine. And so it's always this alkene, electron rich, attacking some sort of delta plus. It doesn't necessarily have to be a hydrogen, but some sort of delta plus atom that is electron poor. Also note the orientation of that HBr relative to the alkene. You can see that the alkene is kind of drawn side on, whereas the HBr is drawn kind of straight on. The reason for that orientation there is because of how the alkene reacts with the HBr. If the HBr was also drawn sort of sideways, you'd have a bit where the delta positive was close to the CC double bond, but also a bit where the delta negative was close to the CC bond. And of course, we have a region of high electron density in the CC bond, so you want to keep the delta negative part away from it so it doesn't repel. It's also really important from a really kind of advanced view of how that alkene interacts with the orbitals on the HBr to break the bond. It has to be attacking from that direction. Once we've then done that, the hydrogen atom that we've made a bond to from that double bond will go onto one of the carbons, but the other carbon is going to be left electron deficient. It's going to be left without having made the maximum number of bonds. So it's going to be positive. We've made a carbocation. Now remember that in our mechanisms, we always have to balance in terms of atoms, but we also have to balance in terms of charge. So we've started off with a neutral electrophile, a neutral nucleophile, we've kicked off Br minus. That second arrow in the first step was to put the electrons onto bromine. So we now end up with a bromine negative, a bromide ion, Br minus. And so therefore, to balance out the charge, we have to have a positive charge in our organic molecule. And so a positive charge goes onto the carbon atom. And remember that carbocations are planar. Then our second arrow, here, our first arrow of the second step is just a really simple arrow where we take the arrow from the lone pair on the bromine, our region of electron density, going to the positively charged carbon that is electron deficient. And so this is an example of an electrophilic addition reaction. In this case, we've taken an alkene and we've converted it into a haloalkane. So you can see how this is a quite synthetically useful reaction. Now, when the double bond isn't in exactly the middle of the chain, or we have something called an asymmetric alkene, there are two possible products, because the hydrogen of the HBr can go onto either of the carbon atoms of the double bond. For the ethene example we've just seen, it didn't matter because the molecule was symmetrical. But we can predict and explain which hydrogen atom, the hydrogen atom will go to which carbon, and which product therefore will be more likely to form using something called the positive inductive effect. Now this is the fact that alkyl groups have a tendency to release electrons. Doesn't mean they have lone pairs or anything like that, or negative charges, but essentially in molecules they tend to sort of push their electrons away from themselves a little bit. And this effect tends to stabilize the positive charge of the intermediate carbocation. So if I have a positively charged carbon, a carbocation, that's then also attached to another carbon atom, maybe there's an alkyl chain going off, that carbon atom that's attached will kind of almost sort of push its electron towards the positive charge, just to kind of help it out a little bit, sort of stabilize the molecule a bit. And so the more alkyl groups we have attached to that positive carbon atom, the more of this positive inductive effect we have, and therefore the more stable the carbocation. And the more stable the carbocation, the more likely that product is to form. So an example. Here we have propanone. This is an unsymmetrical alkene. Our double bond isn't in the exact middle of the chain. And we can draw the exact same mechanistic arrows here reacting with HBr. But the key thing is there's two possible products here. The hydrogen atom that we are making a bond to can either go onto the first carbon, or, as shown at the top, or it can go onto the second carbon, as shown at the bottom. Now, the one at the top is what we call a secondary carbocation, and the one at the bottom is a primary carbocation. And the way that we characterize these is we look at our positive carbon atom, and we look to see how many other carbon atoms are attached to that positive carbon atom. So for the example at the bottom, we have a positively charged carbon atom that's attached to two hydrogen atoms, and then a carbon atom. So that's one carbon atom and therefore a primary carbocation. And it has one positive inductive effect. That carbon atom is going to be able to kind of slightly push its electrons towards that positively charged carbon. The top example is our secondary carbocation. The reason for this is because we have our positively charged carbon attached to one hydrogen and two carbon groups. So this is a secondary carbocation, and we'll have two positive inductive effects because both of those carbon groups can kind of push their electrons towards the positive charge a little bit. So the second step is then the addition of the bromide ion to that positive carbon, and so we end up with two isomeric products. We end up with two bromopropane or one bromopropane. Now, the two bromopropane will be the major product. It will be the product that's formed in more amount, greater yield of that product, because it's come from the more stable carbocation. And the reason why the carbocation is more stable is because it has more positive inductive effects. So a tertiary carbocation is more stable than a secondary, which is more stable than a primary. The one bromopropane, because it came from the primary carbocation, is the minor product. Now the important thing to realise is that you won't just get the two bromopropane forming completely that 100%. You get a mixture of products, but we talk about a major and minor product because the major product might be formed in about 80%, the minor product in about 20%. And this is an example of something that we call regioselectivity. It's which region of the double bond do we add to. We can also do electrophilic addition reactions of alkenes with halogens, dihalogens. Now this might seem a bit odd at first that we can react an alkene with, for example, bromine, Br2, because I said that we have to react it with an electrophile, and electrophiles tend to be electron deficient, have delta positive atoms. Now you might not think that bromine can have a delta positive atom straight away, but remember that at all times the electron density is constantly sort of shifting in molecules. And so at some point there will be a point where most of the electron density is towards one bromine atom and away from the other. And so we have an induced dipole. What that means is that at some stage the bromine atom on the top will be delta positive, on the bottom will be delta negative. So it's not a permanent dipole like we had in the HBr molecule, but it's an induced dipole, but it's still enough for us to be able to react an alkene with. So our alkene is our nucleophile. We draw our arrow going from the CC double bond, the pi bond, to the delta positive bromine atom. This is our electrophile. And then again, the bromine can only have the one bond, so we have to break the bond to the other bromine atom. An arrow going from the bromine-bromine bond, that source of electrons, ending up on the bromine. And so we form a bromide ion, Br-. We have to balance the charge, so we've made our carbocation, our positive carbon atom. And then we draw our arrow like before, from the bromine lone pair or negative charge to the positively charged carbon atom. And so again, it's always this idea of the alkene that's electron rich, attacking a delta positive electron poor atom in the first step. Again, note the orientation of the bromine, it has to be sort of straight on as opposed to side on, like the alkene is. And our second step of it is always the same, with just this kind of charge attraction. And so again, this is a very useful reaction because we've converted an alkene into a di-haloalkane. We've ended up with 1,2-dibromoethane. We can also do the same reaction with sulfuric acid. So again, we have our alkene as our nucleophile. Our sulfuric acid acts as an electrophile. We have a permanent dipole here, where we have our polar OH bond, where we have our delta plus H and our delta negative oxygen. Now you can just draw the sulfuric acid out like that, have the H, have the O, and then just SO3H, to say drawing out the whole structure of sulfuric acid. Again, electron-rich alkene attacking electron-poor delta positive atom. We make our carbocation, and we have this sulfate anion, hydrogen sulfate anion, and then we're going to just have this charge attraction again, this arrow from the negative oxygen to the positive carbon, and so we end up now making this molecule that we call ethyl hydrogen sulfate. And again, notice the orientation of the H2SO4. Now again, this is a very useful synthetic reaction because we can take this hydrogen sulfate molecule that we've made and react it with water. Now this reacts in a nucleophilic substitution reaction. Essentially it kicks off this hydrogen sulfate anion and replaces it with the water. And so the overall reaction of this is that we now end up with an OH group and we regenerate the H2SO4. And so we can write these down as just simple chemical equations. We have our alkene, C2H4, plus H2SO4, forming our ethyl hydrogen sulfate. Then that ethyl hydrogen sulfate can react with water to produce ethanol and sulfuric acid. And if you add those two equations together, you end up with an overall equation. If you have things that are on both sides, so for example, the sulfuric acid is a reactant in one and a product in the other, that can cancel out. The ethyl hydrogen sulfate molecule is a reactant in one and a product in another, they cancel out. And so the overall reaction is to take an alkene plus water and turn it into an alcohol with an acid catalyst. And that again is another really useful reaction. We can turn an alkene into an alcohol. Very, very useful. And also a very useful reaction in terms of making ethanol, which is a very useful alcohol in terms of fuel, for example. Another example is to react it simply with water directly. So rather than doing that kind of two-step through the ethyl hydrogen sulfate molecule, we just react it straight with water. This is exactly the reaction that goes on to make ethanol from ethene. So we take our steam, we take ethene, we have a phosphoric acid catalyst, and we make ethanol. And so the mechanism is exactly the same as we've seen before. The way this works is our electrophile is H3O plus ion. Now this is made from the H plus catalyst, the acid catalyst, reacting with the steam, the H2O. So we have a coordinate bond from the H2O forming to the H plus, the proton. And so this H3O plus is a very electrophilic molecule, much more electrophilic than just the H2O is. But our arrows are exactly the same. From the electron-rich alkene to our delta positive hydrogen atom, then we break that HO bond. We've already got 3 bonds to our oxygen, and we've got already 1 bond to that hydrogen atom, so we have to break the other bond to it. So from the HO bond ending up on the oxygen, again, note the orientation of how I've drawn that. Then we get this carbocation being formed again. Make sure the charge is balanced. So in this example, we've started off overall with a positive charge. We've kicked off water, essentially, and therefore we have to have our positive charge on our carbocation. We then draw an arrow from the lone pair on the water to the positive carbon atom. And then that produces our next step. Now this normally would be where the mechanism ended, but in this case, because we've added water to it, we've added H2O, we now have a positively charged species again, because we have to make sure that our charge balances. This isn't the stable species, and so remember that the acid was a catalyst, and so the final step of it is just to lose an H plus ion. So an arrow going from the OH bond ending up at the electronegative oxygen to regenerate, to lose the H plus, regenerate the catalyst, and we end up with an alcohol. So time to have a go at some questions. If you want to have a go, pause the video and the answers will be on the next slide. And so you have to define an electrophile and to name and outline the mechanism between 2-methylpropanone and water. So the first question was just to define an electrophile. An electrophile is an electron pair acceptor. And then we have to look at the reaction that we were asked to do here. So we draw out our alkene, the 2-methylpropanone. Our electrophile here is actually the water molecule itself. You could of course done this under acid catalyst as well and drawn it as the H3O plus. It's the same thing essentially overall. And so we're going to draw the mechanism again. It's an electrophilic addition mechanism. And so we have our arrow from the double bond, our source of electron rich region, to the delta positive hydrogen atom. And then we've already got the maximum number of bonds for the hydrogen, so we have to kick off the other bond. We have to have an arrow from the OH bond to ending up on the oxygen, the delta negative oxygen. Again, note the orientation of how I've drawn that water compared to the alkene. Again, because this is now an unsymmetrical molecule, we have 2 possible products. We have the hydrogen atom either going on to carbon number 1 or onto carbon number 2. So if it goes into carbon number 1, our carbocation ends up being on the second carbon, and this is actually a tertiary carbocation. It has 3 carbon atoms attached to that positively charged carbon. And what that means is there's 3 positive inductive effects. And I've sort of shown that with these kind of green arrows to show the kind of electron density being pushed towards that positively charged carbon atom. The other way is for the hydrogen atom to go onto the second carbon. In this case, that positively charged carbon atom is now the first carbon, and there's only 1 carbon atom directly attached to it, so it's a primary carbocation. We can then draw the second step of that hydroxide anion that we kicked off in the first step, attacking the fully positive carbocation carbon. And this leads to 2 products, either 2-methylpropan-1-ol or 2-methylpropan-2-ol. Now, the 2-methylpropan-2-ol is the major product because it has come from the more stable carbocation, the tertiary carbocation. It's more stable because it has more positive inductive effects. The 2-methylpropan-1-ol would be the minor product. So thank you for watching this video. You can find many more of these on my YouTube channel. If you found the video helpful, please consider leaving a review on one of the tuition websites. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, feel free to drop me an email. I'm always happy to help.